Hi and welcome to this Applied Maths video. Today we're going to look at an introduction to differential equations. So differential equations are equations that have differential coefficients. So think of a dy dx or a d2y dx squared. In this video, we're just going to focus on introducing how to work with differential equations. There is another video which goes through more of what we see on the exams, the real life differential equations. So linking it back to our forces or for any kind of link to acceleration and so on. So if you want to catch up with that video, it's linked in the description below. So to get us started, there are three different types of differential equations. We have first order with general solutions. So that's where we're not given additional information and we end up with our plus c, our coefficient of integration. The next is first order with definite values. So this is where we're given additional information and we're able to solve fully. And the last is a second order separable. So just something to bear in mind, when we're asked to solve a differential equation, we're always looking to get the variable up here. So in this case, like the y equals on its own. So that's what we mean when we're asked to solve. So y equals, and that may take a little bit of work beyond just the integration itself. It may take a little bit of work with our logs or our indices or even just some algebra work. Before we get into the differential equations, it's really important that you understand how to approach the integration. There is a video linked in the description below that goes through the integration techniques needed here. When we're dealing with any kind of integration in applied maths, I have a little checklist that can be really helpful. So the first thing we want to check is there a formula on page 26? And if there is, use it. But watch out for two bits in particular that we tend to do a very quick backwards chain rule in our head, which is if there's trigonometric functions, so something like sine 3x or cos 2x, or something in the form of 1 over ax plus b. This is a version of 1 over x that needs the chain rule. Now you can use the next method, so use substitution, but it is much nicer and quicker if we can get those two sorted in your head. So just be aware of those. For everything else, it will be exactly as we see it on page 26. The next thing to ask yourself is there or is it a composite function? So remember, a composite function is where we have a function within another function, and this is going to require substitution. So our use substitution method, our focus is on figuring out what has been the inner function and then working backwards. This is our method for going back on complicated chain rule questions. And the last thing we try is integration by parts. Just be aware that this can get very messy if used where composite function use substitution can be used. So it's always a good one to keep for your last option. When we're doing integration by parts, we have a formula on page 26 and you need to be very specific about the order that you approach our questions in. So you've inlate, so INLATE, which tells us inverse comes first, then logarithms, then algebra, then trigonometric, then exponential. One big hint for integration by parts is if you have two of the same type, it is probably not integration by parts. It's going to be something like a composite function. So let's talk about solving first order with general solutions. So this is something that has a dy dx. First order means we have a first derivative in it, so like a dy dx. And it can be worked through. So what we're going to have is our constant of integration, our plus c. So we need to first of all rewrite the equation by separating the x and y or whatever is in the question, because in a real life question they may not be x and y's, and we separate them to different sides. So separate your variables. We will only have two variables. Then we integrate both sides. And then remember, solving means getting the y on its own or whatever is in that top line of the differential or the differential coefficient, the dy dx, whatever is in the top. This is our focus. That's what we want to get on our own when we're solving. So let's take a really basic example here. solve this differential equation. So the first thing we're going to do is we're going to separate it out, meaning the dx is going to come up. But at the same time, this y is going to move over. We want to get the x's on one side and the y's on the other. Because of how integration works with our integral, with our dx or our dy, it's really important that all you do at this step is multiply or divide. There should be absolutely no adding or subtracting. So this becomes 1 over y dy equals 4x dx. So you're only ever thinking about multiplying or dividing. And we'll see a few different examples of where maybe you have to do some factorization to bring it to that kind of multiplication or division. But just be very, very mindful. You should never be adding or subtracting at this point. We are now going to integrate both sides. We've been given no additional information, so there are no limits of integration here. So we have to put in our plus c. So look at each side separately and see how are we going to integrate it. So on the left-hand side, we go to page 26, and this will become the natural log of y. And then on the right-hand side, we get just a normal polynomial, which means we add 1 to our power, divide by our new power, plus c. You can put your plus c in here, you can put your plus c in the end. It doesn't really matter once the plus c goes in. I like to put it in a little bit early because otherwise I might forget it. So this becomes 2x squared plus c. We're not finished because go back to the question. We're asked to solve. So we're trying to get this top variable, this y, on its own. So what we're going to do is we're going to take e to the power of both sides. E to the power of natural log disappears. You can use any version of your laws of logs here. That's fine. So y equals e to the power of 2x squared plus c. If you want to kind of clean that up, that's fine. 2x squared times e to the power of c. That's also fine. Where that c goes will change what the c value is, but it's absolutely fine to put that in anywhere. It is possible to put that plus c in slightly differently, so I just want to show you that very quickly. So if we work through this in the same way, so we get our natural log of y equals, here we get 4x squared over 2. You can either put in that plus c now, like we did. You can put it in and kind of work with it, like I'll show you here. So plus c, and then you go ln y equals 2x squared plus c, and then here we get y equals e to the power of 2x squared plus c. So one option is to kind of remember that that constant is still a constant no matter what you do with it, and it just remains a plus c. I don't particularly like that method. I think it's confusing because you're not applying our normal rules of equations in that situation. So kind of if you don't want that plus c in too early, one option is that we work through without the c until you get to y, which can be a little bit easier for students. And then when you get to your answer, which is this, you put in your plus c. So it looks different. That answer looks different to our previous one. But the reason it looks different is both of those c's will give different values. But the final answer when you plug in those c's would be the same. So both of these are absolutely valid. If you decide to go down that route, just be so careful to make sure to put that plus c in. Generally, we're not going to see these general solution ones as much on a paper as we will with the definite values, because in a real life situation, it's going to be a lot more common for us to have additional values and want a definite answer. So let's look at another one like that, but a little bit trickier. So here we have a little bit more going on. We need to separate them out. So we're going to bring our dx over. X's are going to stay on that side. We're going to bring the y back over, and this whole bracket that has already very nicely been pulled out for us is going to come over as well. So that means I had a y squared dy already here. I brought over the other y, and that goes under the line here. I'm dividing by that. On the right hand side, I had a 4x with a dx brought over, and then I brought over this bracket, this x squared plus 1, And when we bring over that x squared plus 1, we are dividing by that. So let's do a little bit of cleanup. So here on the right hand side, that tidies to y dy equals 4x over x squared plus 1 dx. Everything is lovely and separate, and now we break it up. In an exam question, you're going to get your marks for your separation. So it's really, really important that you show that really, really clearly and you put the time into it. If you separate incorrectly, you're going to create something that may be impossible for you to integrate, or may just, if it can be integrated, take you a very long time, which is going to hinder you in an exam. So do take your time and do a lot of practice on these. On the left-hand side, we have just a normal polynomial. So we're going to integrate this as y squared over 2 equals. Now, this right-hand side, it looks a bit more complicated. So we're going to go to our checklist. So is there a formula on page 26? And the answer is no, there isn't. Nothing straight. It has to, when I ask, is there a formula on page 26? We want it to look exactly like 26. With our two little exceptions, trigonometric functions and anything in the form 1 over ax plus b. This has a power on the x underneath the line, so it's definitely not that. So then we ask, is it a composite function? So it might be hard to see, but this is a composite function. Now, if you get confused with that and say, I don't know if I can see that as a composite function, what I would say to you is, it's definitely not integration by parts, because integration by parts is needed for anything multiplied together. So if there was 2 bits, and you could argue that this is a 4x multiplied by x squared plus 1 to the power of -1, yes. However, integration by parts should only be used by us if there are 2 different types of pieces. So for example, here we have algebra and algebra. That would not be integration by parts. So this is our u substitution. So what I'm going to do is I'm going to take this piece and I'm going to just work it over here. And then I'll bring it back when I have done my work on it. You're welcome to work within the question. I like just to have a bit more space. So again, this can be tricky to see, is it u substitution? And it is. And the thing we want to sub in, or the thing we want is generally going to be the more complicated piece. So we have a 4x and we have an x squared plus 1. So I'm going to let u be x squared plus 1 because it is more complicated. That gives us a du dx of 2x, which gives us a du of 2x dx. And we can do a little bit of work with this, because now if we go to look at this integral, I can have a 2x all over u dx. And then this part here, 2x dx, can be simply replaced with a du. So you're doing 2 things with our u substitution. You're trying to make sure that you change all of your variables, but you also need to change that dx into a du at the same time. So this becomes 2 over u du, which is what we want to integrate. So that 2 can be pulled out in front if you want, or you can leave it there. So that's 2 natural log of u. So then when we put it back in here on our, where we were working on the left hand side, that is 2 natural log. Instead of u, I'm going to put back in what I used for my substitution, which was x squared plus 1, and I also have a plus c. So this is our composite function using substitution. I'm not finished yet because this differential equation needs y equals. So we're going to do a little bit more work to tidy that up. So y squared equals 4 ln x squared plus 1 plus 2c. And then to get y on its own, we're just going to square root this whole part. And that's our answer. Is it fully correct? So just be careful One thing that you have to be mindful of when you put in a square root is to take account of the fact that we always need to put our plus or our minus in front of that, because we're basically, we started with a quadratic. We have a y squared equals, so we're going to have to get two answers. So we need to put that plus and minus. Really good rule of thumb is when you apply a square root, you need to apply a plus and minus. We get out of habits of this because a lot of times when we've met this, when we start in maths, maybe first year, second year, and we're using this idea of putting a square root on both sides, we're doing something like Pythagoras, which is very practical and only has a positive answer. So we lose that sense of it. So just be careful. Additionally, if you would prefer to put that c in later, you would end up with something like this. So you would have your 4 ln x squared plus 1 in your square root, and then you just put a plus c there at the end. If you find the c coming in too early is confusing you, that's fine. Leave it till the end, put it in. However, don't forget to put it in. So this is our last first order with general solutions. Very straightforward to separate. So step one, we separate. So I have dy equal natural log x dx. Now, that might seem like, oh, lovely question. However, when we go to actually try and integrate that right-hand side, so left-hand side is fine, it's perfect. The integral of dy is just y. Is there a formula on page 26? No. We have 1 over x integrates to ln x, but we don't have a way to integrate ln x. So then, is there a composite function? It's like, well, no, ln x is completely basic. There is an x within a natural log, and that is just a normal function. There is no composite. If it was like a 3x or a 5x, yes. But at this point, no. So our only option here is actually integration by parts. And this is one that's good to see, to integrate that natural log and make sure that you're happy with it, because it could throw you in an exam and think, what am I missing? So let's bring this to the side, and we're going to do an integration by parts. Now you might be going, how is it an integration by parts? There's a lot of bits missing. So let's go get our formula and let's try understand what's going on. So from page 26, we get the integral of u dv equals uv minus the integral of v du. So all we're going to do to break this up is we're going to use our ln x as our u and our dx as our dv. And you might be going, well, why? Well, think about what's not written there. There can be a 1 put in here. I'm going to just break this out a little bit so I have a bit of space. So I'll move my dx over here a little bit. So imagine I have the 1 here, and that becomes your second part. We always break up our integration by parts in a very specific order, and that is IN, L, A, T, E, INLATE, which basically stands for inverse, logs, algebra, trigonometric, and exponential. The first piece is a log, that's obvious, ln. However, the second piece is algebraic. And that might be how is one algebraic? But think about what 1 means in the context of integration, because 1 is within our polynomials. 1 is something when we integrate it, we get back to a 1x or 1 of whatever variable we have. If we were to differentiate it, we differentiate 1 the same way we would differentiate any constant. So like an x to the power of 0, we would end up with nothing. So it does fall under algebra. So there are 2 bits, it's just hard to see. So like I said, this is a nice one to see explicitly and work through it, because it's one that may not be obvious if you were just faced with it in an exam. So we have u equals ln x, and that's great because now I'm differentiating, and we do have a rule for differentiating our natural log, and that's 1 over x, and that becomes du equals 1 over x dx. We then have dv equals 1 dx or just dx, and then you integrate and v equals x. So then if we want to actually integrate that, we want to, I'll move down here, u by v, which is ln x, by v, which is x, minus the integral of v x with du. So that's 1 over x dx. They simplify to simply 1. So we end up with our final answer here as x ln x minus the integral of dx, which is just x. So putting that back over here, x ln x minus x, and then we need to finish it with the lovely plus c, and we're done. So that, again, just a bit of practice on your integration is so important. Differential equations, the differential equation part really is that separation, which is tricky and does need a bit of work, but you're going to get nowhere with this unless your integration is really, really strong. Our integration that we're doing in applied maths is so much more than you see in maths. So what you do in maths is not going to get you through. You need to be very confident on not just how to do the integration, but how to recognize what integration that it is. So if you need to, go back to the integration techniques video linked in the description below and practice that. Make sure you're happy with your U substitution. Make sure you're happy with your integration by parts. Get on top of it. Okay, so now we're going to look at solving first order with definite values. This is a lot more common when it comes to what we're going to see in the exam questions. So they're going to do something like, oh, x equals something when y equals something. And that when is so important. So there are two methods for approaching this. The first one is the constant of integration. Now, from the integration we do in maths, it is a lot more basic. But when we are given values, the plus c method is generally the way we approach it. However, because of what we're doing in applied maths and how we're working, the limits of integration method can be a much nicer, more efficient approach. There's less to do, there's less messing about. I would much prefer it, and that's the method that I'm going to stick to with this video. However, if you want to use the plus C method, here are the steps. So feel free to screenshot this and you have it. So you're going to basically work through the way we did, and then similar to the method you use in maths, you're going to sub in your values for x and y to find a value for c, and then you rewrite your answer. It's absolutely fine, but it is not the most efficient method. It is slow. So instead, we're going to use option 2, which is using limits of integration. It is just so neat and tidy. So first thing we're going to do, we're going to rewrite the equation by separating it out. That's exactly as we have been doing. We're going to integrate both sides of the equation, and we're going to now include our limits. When we're working through our example, we'll talk about how to make sure the limits match, how to make sure they go in the right place, and so on. Now we solve, which basically means when we work through our evaluation step, we want to still get that idea of whatever the variable is on the top, usually the y, and get y equals as our answer. So again, 3 steps versus our previous steps. So this is what a first order with definite value looks like. It says solve the differential equation dy dx equals 2y. But they then say, given that y equals 1 when x equals 0. So we're given these additional bits of information, meaning we won't need a general answer. We won't need to leave it with a plus c. We will be able to go a little bit further and get an actual answer. So step 1 is we separate. So I'm going to bring that dx over. So I'm going to bring the dx over here, and I'm also going to bring the y over. So that's going to be 1 over y. And then this becomes 2 dx. I try to leave any like numbers, coefficients on their own, constants as it becomes. I'm going to try leave those above the line if I can. I don't tend to bring that with the y. And the reason is, if I bring that 2 with the y, it becomes like a mini composite function, and I don't particularly want to deal with that. So instead I leave it. So then we apply our integration. So far it is exactly the same. Now, this is where it's different. When we want to apply our limits, we are told that y equals 1 when equals 0, meaning when y is 1, and I put that at the bottom, x is 0. They have to be at the same line. So they're both at the bottom of our integral. Okay, so when y equals 1, x equals 0. Now, we are going to then make sure that we still get an equation answer, meaning we still have x and y. So we put, and then the top of it is y equals y when x equals x. So that keeps the variables there. So all we're doing is, rather than putting in a plus c, we're using our limits to say, okay, we're going to evaluate with our limits y is equal to 1 when x equals to 0. Then we integrate as normal, so we get ln y, and we're now going to evaluate that between y and 1. And then on the right hand side, we get 2x to the power of 1 divided by 1, and we're going to evaluate that between x and 0. So this is ln y minus ln 1 equals 2x minus 2 times 0. Be really careful with the 0. One thing that tends to go wrong for students is they assume when they put in a 0, everything disappears. A lot of times that is true. However, think of times where it doesn't happen. So if you have a power of x, so if you have an exponential of sorts, when you plug in a 0, anything to the power of 0 is 1. Cos of 0 is 1. So just be really, really careful. So 2 times 0 is 0, and I'm going to put a line through it because I know that that's gone. ln 1, natural log of 1 is 0, so that's also gone. So we're getting ln y equals 2x. There's no need for a plus c because I had some definite values. I evaluated y equals 1 when x equals 0. So if there's a constant, it will come through here. And then to get rid of my natural log, I like to use the shortcut of taking e to the power of both sides. E to the power of ln, that undoes itself, so y equals e to the power of 2x. However you do that, it's fine, and that's our final answer. This is, like I said, the one we're going to see more in our papers. We're not going to have a plus c, there won't be constants, we want to use those limits to set that up. So let's take a slightly different example and see, can we work with this again? If you want, pause the video, see can you set it up, and then let's work through it together. So I'm going to bring my dx up, I'm going to bring my y over. Sometimes separation can be the most difficult part for students as they get more and more challenging. So do a bit of practice on all the steps before putting it together. So bring my y over, it's 1 over y dy. Bring over my dx, I get x dx. Now, given that y equals 3 when x equals 0, and that goes y to x. This is ln y. I'm evaluating that between y and 3, and this turns into x squared over 2. I'm evaluating that between x and 0. ln y minus ln 3 equals x squared over 2 minus 0 squared over 2. I do like to show it mentally to know that all is going okay, that I haven't accidentally left out a piece. So as you get kind of better at these, you might decide to not put in your substitution of 0, but just be so careful if you decide that that's the case. Okay. To get y in its own, we need to apply the e to a power. Now, I like to work this kind of e to a power piece. If you want to do it differently, absolutely. E to the power of ln undoes itself, so we're left with y equals. Be careful here. This is e to the power of x squared over 2 plus the natural log of 3. E is not distributive. You cannot put E on all 3 pieces. That is not how it works, okay? When we do powers or anything like that, think of your squares, your square roots. You have to do it to the full side. However, what we can do now is on that right-hand side, we can break that up using our rules of indices. That is law 1. So we get x squared over 2, and that's going to be multiplied by e to the power of ln 3, which this will tidy up to simply 3. So y is equal to 3 e to the power of x squared over 2. So try to really bear in mind when you're doing this not to do something silly like apply an e to all 3 parts. The e, if you're going to do that e to a power applying an ln, it has to go on each side. And then when you tidy it up, you're using the laws of your indices. You're not just making things up or doing something silly. So given the differential equation, dy dx equals xy squared plus 4x, and the y equals 2 and x equals 1. Find the value of y correct 2 decimal places when x equals 2. So we're going to use limits to set up this full question. We have that extra piece of information where they told us x equals 2 and we want to solve for y. So rather than getting y equals and an answer in terms of x, this time we're going to be just getting a value. The separation here is going to be a little bit different because you have to get rid of the y squared, but you can't do it currently as is because you have this plus 4. So we need to be really, really careful when we're doing any type of separation that the separation is multiplication or division. If there is adding there, we need to think in terms of creating a multiplication or division. And the easiest way to create a multiplication is to factorize. So what we're going to do here on the right hand side is we're going to pull out the x, which gives us a y squared plus 4. And now what I'm going to do is I'm going to bring this dx over and I'm going to bring this bracket over to the other side. I'm dividing by my bracket, so I get 1 over y squared plus 4 dy equals x dx. We're then going to integrate both sides. So we're told that y equals 2 when x equals 1. And we want to find the value of y when x equals 2. So this is how we set up our limits. We put in everything we have, and when we get through our whole question, we'll just have an answer for y. This is what I keep saying about limits being really, really efficient to use. So the left-hand side, so go back through our checklist. Is there a formula on page 26 that will allow us to work with y squared plus 4? And the answer is yes. It is the middle box on page 26, and it's the last one down. And it's the one that gives us, I'll write it up here, f of x equals 1 over x squared plus a squared. And that will go to, the integral of f of x dx will equal 1 over a tan inverse x over a. So for us on that left-hand side, we end up with 1 over a, which is 2, because 4 is a squared. And then you have tan inverse of x, which in our case is actually a y, over a, which is 2. And then this has to be evaluated between y and 2. And on the right hand side, just a normal polynomial, add 1 to our power, divide by our power, and evaluate that between 2 and 1. So we get a half tan inverse y over 2 minus a half tan inverse 2 over 2 equals 2 squared over 2 minus 1 squared over 2. Now, a big warning here. As soon as you see anything trigonometric, you need to remember that we always work in radians when we're working in calculus. And I go through that in a little bit more detail in the integration techniques video. So what you need to be careful of is this thing here in particular, which is tan inverse of 1. It's not 45 degrees, it's pi over 4 radians. So just be really, really careful. When you're working, make sure that you're constantly checking your mode of your calculator. Is it in degrees or radians before you type in sine, cos, tan, or any of their inverses. I prefer to use page 13 to kind of help me with this. I think it makes it a little bit nicer and neater. It means I'm not messing with my calculator as much, but completely up to you. Let's do the right hand side cleanup. So we have 4 divided by 2, that's 2 minus a half. So this gives us 3 over 2. To tidy everything up, I'm just going to multiply across by 2. So that gives us tan inverse of y over 2 is equal to 3 plus pi over 4. So we have a little bit more work to do. Remember, we're trying to find the value of y. So we're going to bring that tan inverse across. When it comes across, it becomes tan. So we're going to do the tan of 3 plus pi over 4. So y is equal to, bring that 2 across, y is equal to 2 tan 3 plus pi over 4. You can start messing around with identities here if you really want to use page 13. However, it's going to be much more efficient to go to your calculator. Make sure you're in radian mode. It's really important for both higher level maths and applied maths that you're quick at changing your mode, that you know how to do it and you feel very confident with it. So get this into your calculator. And we're getting 1.5, and that's our final answer. So the limits, if we were working with plus c, we'd have to find our plus c and then do a second substitution. Limits is just such an efficient way for us to work. So just be very careful. Even though the question doesn't start with trigonometry, we can often get trigonometric pieces come in when we do our integration. So make sure you remember that piece about radians. So the last type of differential equation we're going to look at here is a second order, which can be reduced to a first order. So separable second order differential equations. So a second order is a differential equation that has both a dy dx, but also a dy over dx squared. So a first and a second derivative coefficient. And it'll only have two variables. So in order to work with this, the first thing we're going to do is we're going to let dy dx or equivalent, because again, in a real world situation, that could be they could be any variables. So we're going to let that equal to v, which means then when we differentiate v with respect to x, it is effectively equal to that second derivative. We're going to treat this equation as a first order, solve for v, and then we're going to go back and do a quick substitution for dy dx in for v and do the first order again. So for these second orders, we're effectively going to create the question twice. We're going to complete the question twice. We're going to break it down to a first order, solve that first order, so back in to make a new first order and solve that first order. These are going to be less common in the real world. So one example of where we might have a second order would be something like acceleration linked with displacement, because displacement is going to be differentiated twice to get to acceleration. There are other examples, but like I said, it will be less common. So let's jump into looking at how we would do this. So here's our second order differential equation, d2y dx squared equals 3 dy dx, and it's given us some values that we need to work with. So first thing is identifying that it is second order. The next thing is understanding what all of these mean. So we have a y equals 0, we have a dy dx equals 1, and we have an x equals 0. So our first step is to simplify. So what we're going to do to simplify, we let v equal dy dx, which in turn means differentiating v with respect to x is the same as the second derivative, d2y dx squared. Meaning we can rewrite this as, instead of the second derivative, dv dx equals 3 times v. And now we have a really nice little first order we can work with. The other thing I like to do is to rename this middle piece, because it says dy dx, so we're going to say that's v equals 1. So let's separate this out. dv, we bring the v over, we leave the 3 where it is, and bring our dx across. We integrate both sides. We're told that v equals 1 when x equals 0. So go for v to x, just like we would normally. This is ln v. We're going to evaluate that between 1 and v. This becomes 3x, and we're going to evaluate that between x and 0. That is ln v minus ln 1 equals 3x minus 3 times 0. ln 1 is 0, 3 times 0 is 0. So we end up with ln v equals 3x. So v is equal to e to the power of 3x. Now, we are done with solving that first order, but we're going to go back and remind ourselves that actually v is equal to dy dx. So dy dx is actually equal to e to the power of 3x. Let's separate that, e to the power of 3x dx, and now let's integrate. We were told that y equals 0 when x equals 0, and let's integrate this. So y equals, and if we want to integrate e to the power of 3x, it stays e to the power of 3x, but we end up dividing it by the derivative of the inner function, which is the derivative of 3x, and we evaluate this between 0 and x. So this is going to become y equals e to the power of 3x over 3 minus e to the power of 3 times 0 over 3. This is one we need to be careful with because we end up with e to the power of 3x minus e to the power of 0, which is 1 all over 3, and that is our final answer. So they're not very difficult. They are a little bit longer. Just bear in mind for that second order, you break it down to a first order, solve it, and then create another first order and solve that. Thank you very much for watching this video. Hopefully you found it helpful. The other related videos are linked in the description below.